Hello, my dear friends. I am Dr. Tito, a Finnish word meaning knowledge. I always remain in search of knowledge, and I want to share with you what I have learned so far. And today our target is to study the lithium onwards molecule. Basically, at first we will study the lithium from lithium to nitrogen, and then we will study oxygen molecule, and then we will conclude our journey of molecular orbital primarily, and then we will move to some other section. Okay, so let's first start today lithium. So our target is to draw the relative energy level diagram for the diatomic Li2 species, and as you know, it will be formed from the two lithium atom, of course, and lithium atom has the electronic configuration 1s2 2s1. It has atomic number 3 and it has electronic configuration 1s2 2s1. So what is something new here is the involvement of the 2s orbital, and with introduction of the principal component number 2 we will get additional 2 atomic orbital, that is 2s and 2p atomic orbital. Up to helium we were actually confined up to 1s atomic orbital. Now we will have to consider the combination of the 2s and 2p atomic orbital also. Now, as before, if we consider Li2 molecule, as before, here the 1s atomic orbital will combine just like hydrogen and helium to generate two sigma molecular orbital, that is sigma 1s and sigma star 1s, but these both molecular orbital will be completely filled, just as it was in case of helium. You just remember, in case of helium it was 1s2. So ultimately, and here if we consider the 1s2 up to the 1s2 level, we will get the electronic configuration of the molecular orbital just like this, that 1s2 and sigma 1s2 and sigma star 1s2. But so ultimately in the bonding molecular orbital there will occur 2 electrons, and in the antibonding molecular orbital there will occur the same number of the electron, that is 2. So ultimately number of the electrons in the bonding and antibonding molecular orbitals are same, and that is why what will happen, the bond order will be 0. That indicates there occurs no bond formation. That means in case of lithium 2, this inner 1s orbital will contribute nothing to the ultimate bonding, and I am telling this about lithium, and this is actually valid for all lithium onwards molecule. Now so there is no any role of 1s2 orbital. So in case of 1s orbital, okay, there is no any role of 1s orbital. So you just remember, in case of lithium, just like lithium, so the outer electron, that is the valence electron, you know from your very so class 10 onwards, that is the valence electrons. Valence electron are actually responsible for the formation of the molecule, that is the formation of the bonding. Valence electron are always responsible. So here the valence shell has a principal quantum number 2, and that is why we will confine ourselves only on 2s and 2p atomic orbital. We will remain restricted to the discussion of the 2s and 2p orbital, and these 2s and 2p, just I am again repeating, these 2s and 2p orbitals are mostly responsible for the formation of the bonding between the different atoms. We are actually discussing only the diatomic species, so different diatomic species will be formed by the combination of the 2s and 2p orbital in case of lithium onwards molecule. Okay, so let's continue. So we will now consider only the formation of the different molecular orbitals from the 2s and 2p atomic orbital, and we will ignore the 1s orbital. This is the conclusion. Now let us clear the canvas. Okay, so from the 2s you know, from the 2s, as just before, it is same as that of the 1s orbital. From 2s, from the 2 lithium atom we will get 2s orbital. So similarly, so here from the 2 lithium atoms say we will get 2 atomic orbital, and again 2 molecular orbital, of course, overlap of s orbital will give rise to the sigma interactions, and we will have sigma 2s bonding molecular orbital and sigma star 2s anti-bonding molecular orbital, just we got in case of 1s orbital. But we have to consider differently the case of the p orbital. Now in case of the p orbital, what will happen? I am again erasing. In case of p orbital, now the number of the p orbitals are 3. You know, number of the p orbitals are 3. So 3 p orbitals are there, and we have discussed earlier that if we take x axis is the molecular axis, then px orbital will form the sigma bond, and if we take the z axis as the molecular axis, then pz orbital will form the sigma bond, and corresponding sigma star 2px or 2pz orbital will be formed. And if we the remaining two always will form the pi orbital, because in that case lateral overlap will occur. So in case of p orbital, so 3 from one lithium atom we will get 3 p orbital, from another lithium atom, lithium or lithium like atom which has the 2 p orbitals, we will get another 3 p orbitals. From the 2 atoms altogether we will get 6 p orbitals, and you know from your early classes that the number of the molecular orbitals will always be same as that of the number of the participating atomic orbitals. So here altogether 3 plus 3, 6 atomic orbitals are there. So we will expect 6 molecular formation of the 6 molecular orbitals. So at first we will expect that say x axis is the molecular x axis, molecular axis. Say we have considered x axis is the molecular axis. Then px will form the sigma bond, and sigma bond is stronger, and it will have the bonding orbital will have the lowest energy. Since it is the most strongest, it will have the lowest energy, and again more energy is needed to rupture this bond or to break the bonds, and hence anti-bonding sigma bond will also have the highest energy, since high energy is needed to break the sigma bond. Okay, so this is sigma bond. One p orbital will form the sigma bond. Which p orbital? Here in this case we have considered this p orbital will be 2px, because the molecular axis is the x axis. 2px orbital will form the sigma bond, and remaining other 2 p orbitals are of course 2py and 2pz, and one sigma bond will be formed, and remaining 2 will of course form the pi bond due to the lateral overlap. In one case there will occur the head-on overlap leading to the formation of the sigma bond. In other 2 cases we will get the 2 pi bonds. Okay, so here we will get actually another 2 pi bond. So here, and that 2 pi bond will have the same energy, and same energy, if there occurs 2 orbitals having the same energy, we we designate these 2 or more orbitals as the degenerate level of orbitals. So these 2 molecular orbitals are the degenerate because these 2 have the same energy. So this is pi and this is pi orbitals, and if we designate this is as pi 2py, and this will be of course 2 pi z, pi 2pz. So these pi orbitals has been formed from the 2pz atomic orbital, and here this pi orbital has been formed from the 2py atomic orbitals, and these all are the bonding because it has the lower energy than the isolated atomic orbital. You see, actually I have this is the in this direction I have labeled the energy level, and this is the energy level of the isolated orbital, atomic orbital, and this is the energy levels of different molecular orbitals. So this is all are the bonding, lower energy bonding molecular orbitals. So 1 sigma to px, 1 sigma to px and 2 pi orbitals, 2 pi bonding orbitals. And here again similarly 2 py and 2 pz, since 2 bonding molecular orbital has been formed, corresponding of course to anti-bonding molecular orbital, pi molecular orbital will obviously form. If there occurs bonding, of course the other pair, that is the anti-bonding, will must come into existence. So here we will get, again to degenerate, of course the energy level is same, just remember, to degenerate pi, here this is pi and this is 2py say, and this will be 2pz, and since these are anti-bonding, this must be designated as asterisk. So pi star 2py, pi star 2pz, and this should be sigma 2px star. So this is sigma, this is actually sigma anti-bonding molecular orbital, these are the pi anti-bonding molecular orbital, and in the lower level it is bonding molecular orbital. So in this way different type of molecular orbitals will be formed from the interactions of the p orbitals. So now in case of lithium onward molecules where there occurs 2s and 2p orbitals, the total complete picture, the pictorial representation of the energy level diagram will be like this. I am clearing this and again I am drawing. So say lithium onwards molecule, there will occur 2s, so I am just drawing 2s here and 2s, 2p here. So say this is one atom, and in case of diatomic species there will occur another atom. So this is say another atom, this is 2s of the another atom, this is 2p of the another atom. Okay, say if you consider lithium, here it will write, you will write lithium atom, here you will write another lithium atom. I am not writing because I am just trying to draw a general scheme which will be valid up to nitrogen. Okay, now this is 2s and this is 2s, and these two 2s will interact, and these 3 and 2p, this is 2p, will interact, leading to generate different molecular orbital. The pictorial representation will be like this. Okay, now I am trying to join all these using green pen. So this would join, so this is sigma 2s, this will be of course sigma star 2s, and this will be sigma 2p. I am not mentioning px, py or pz. If you take pz as molecular axis, it will be pz. If you take px as the molecular axis, this will be px, and remaining two will be pi orbitals. So this is pi 2p, these two are pi 2p, and here these two are pi star 2p, both are pi star 2p, and this is sigma star 2p. And now join all these, and just here you join the pi. Yes, in this way we join all these things, and here actually I have in the along the y-axis I have tried to mention the energy. Along this way energy is increasing, 2s has lower energy than 2p, and 2s is in the lower and 2p, and the energy level diagrams of the energy levels of the different molecular orbitals are in this way. But here one point need to be remember, it is very important. In this region you see the energy of the sigma bond of course is lower than the pi bond, pi molecular orbitals. Sigma molecular orbital has lower energy than the pi molecular orbital, and sigma 2p has lower energy than 2 pi orbitals. But this energy difference is not very high. There are some other factors which can contribute also, and they will contribute in such a way that it may occur that in some cases these two pi orbitals actually may lower in energy than the corresponding sigma orbitals, and in those cases the energy level diagram actually will change to some extent. And this energy level diagram which I have already drawn here, that is, this is say first case 1, and this is say case 2. In case 1, this case 1 type of energy level diagram, molecular orbital, is valid for, it is very important, you should remember, oxygen onwards molecule, oxygen onwards molecule, it is valid. Okay, that is the molecule consisting of atom having atomic number greater than or equal to 8, having greater than or equals to 8. So greater than or equal to 8. Okay. Now you just remember, but in case of molecule consisting of atom having atomic number lower than 8, that is from lithium to nitrogen diatomic species, I mean lithium atom to nitrogen atom, if you consider it has atomic number lower than oxygen, and in those cases from lithium to nitrogen, actually this case 2 type energy level diagram is followed. So now so in case of oxygen what will happen? In case of oxygen, case 1 type, but in case of lithium to nitrogen, case 2 type molecular orbital will be valid. I am rewriting again, drawing the other type of case 2 type of molecular orbitals which will be valid from the lithium to nitrogen. Okay, so I am clearing this canvas. So I am drawing this in red color. So 2s, say this is 2s, as before it is same. So here 2p, what I have told, that in case of lithium to nitrogen, the energy level of the pi orbital will be lower than the sigma orbital. So the structure will look like this. So this is say sigma 2s, this will be sigma star 2s, and this will be pi, now in lower energy than sigma, and this is sigma 2p, and this is this will remain same as before. So this is sigma pi star 2p, and this is sigma star 2p. So you now join all these things together, and together you will join all these things together in this way, and you will get the pictorial representation of the relative energy level from the lithium to nitrogen. So this is 2s, this is 2s, this is 2p, and this is 2p, and this is the energy. We have drawn the energy level along y axis. So in this way. Okay. Now you consider the lithium Li2, whether the formation of this molecule is possible from 2 Li atoms or not. So as we have told before, that we will consider only the 2s. So it has valence shell only we will consider. So in case of one lithium atom has the atomic electronic configuration 1:2s1, we will focus only on this 2s valence shell, 2s electron. So in case of lithium, these two, in case of lithium what will happen? So we will get 2 electrons from each lithium atoms. So So in case of Li2 molecule will get altogether 2 electrons from each contributing atom. Each atom will contribute 1 electron. So from here we will get from here here there will be it is 2s1 and it is 2s1. So 2 lithium atoms. Say this is the relative energy level diagram of the lithium atom. Okay, so 2s1, and now in the molecule, of course, there will have altogether 2 electrons. Now where this 2 electron will reside? Of course, it will reside in the lowest energy sigma 2s orbital. So the electronic configuration of lithium is sigma 2s2. It is very easy, and all other molecular orbital will remain vacant. So what will be its bond order? Its bond order will be number of the electron in the bonding molecular orbital and number of the electron in the anti-bonding molecular orbital, and this the result will be divided by 2. So half of number of the electron in the bonding molecular orbital in that is in sigma 2s, it is 2 minus 0. So no electron will occur in the anti-bonding molecular orbital. So 2 minus 2 is 0. So it is ultimately 1. So a single bond is possible between 2 lithium atoms. Single bond is possible. So thus its formation is possible, and indeed it has been detected in Li2 species has been detected in vapor phase. Okay. So we are actually predicting from molecular orbital theory its existence, and it's really happened in experiment. Okay, we have realized it in experiment.